Hi ladies and gentlemen, let me wholeheartedly welcome you to the fifth video in this series. In this video we will discuss about some useful discrete signals. So in the last two videos we have understood the frequency of continuous time signals and frequency of discrete time signals. So we understood that the frequency of a discrete time signal, that is a number of cycles per sample or inverse of the number of samples per cycle. So here we will see some useful discrete signals. We will simulate them with Python. The contents of this video is your learning outcomes. Then we will see the unit delta signal, then the unit step signal, the ramp signal, the triangular signal, and the summary of understanding. In between we will see some simulations with Python. So your learning outcome here is you will learn the different singular discrete signals and realize them in Python. Now let's think about a unit delta signal. This is somewhat similar to the canonical delta function we saw in the analog domain. So here the unit delta signal is defined as u of n. Here the time axis is discrete, that is n. U of n is 1 for n equal to 0 else. So the shape of the signal looks like this. For minus infinity to minus 1, the value is 0. 1 to infinity, the value is 0. At n equal to 0, the value is a 1. Okay, this is a discrete unit delta signal. And when you think about a unit step signal, is defined as u of n. Here also the time axis is discrete. U of n is 1 for n greater than or equal to 0 for n less than 0. Here you must note one point. Here this function has value at n equal to 0. Un is 1 for n greater than or equal to 0. For n equal to 0 also I have the function value, that is 1. This is in direct contrast with your unit step signal in the continuous time domain, where value at t equal to 0 is not defined. But here the value at n equal to 0 is defined, that is unity. So this is the shape of the signal, that is from minus infinity to minus 1 the value is 0, and from 0 to infinity the value is a 1. So this is the unit step signal. And you can see that this unit step signal can be obtained from many delta functions. That is, these are delayed impulses. So I from 0 to infinity, delta n minus I, that will be un. Or delta n will un minus 1. Because if I delay un by 1 unit, this will appear here. So if I take un minus 1, it will be a delta function. Now there is a ramp signal. The ramp signal is defined as r of n, that is n un. That is, for n less than 0, the function is 0. For n greater than or equal to 0, it is n. That is, when n equal to 0, it is 0. N equal to 1, it is 1. N equal to 2, it is 2, that way. That is a unit ramp signal. Then there is the triangular signal. The triangular signal is defined as a tri of n. That is, n for n 0 less than n by 2. I assume that a capital N is an even number. Or else it is a minus n for n by 2 less than n. So here this increases like this. Okay, here from 0 to n by 2, this has a positive slope n, and from n by 2 to n, it has a negative slope. So you have a triangular signal like this. Then we will see the simulation in Python. This is how I make an impulse signal. This is an impulse signal in the discrete domain, where it reads in a discrete axis n, a time axis n. It returns nb dot concatenate 1 comma nb dot zeros len n. So likewise, what I have made is an approximation of the impulse signal, though there is 1 followed by many zeros. So I have an axis here that is 0 to 10 is to 1. That is, it's a vector starting with 0, 1, 2, 3, etc., ending in 9. So I make an axis for the impulse function, that is a list range 0, len imb n. So that is the axis. So I plot this imb n against axis. And then I put a grid on the graph and show the graph. I will run it in a IPython terminal. I will zoom in a little. Here I invoke an IPython 3, and the name of the function is imbfunc. So I run imbfunc.py. Now you can see that there is a unit impulse happening here. At n equal to 0, there is an impulse of height 1. Everywhere else it is a 0. So this is how we simulate an impulse function. Then I go to another function, say I see many codes here. Now I can have a ramp signal here. So this returns a list of values from 0 to len. So this is a ramp signal. So what it returns is range 0, len. So this ramp n function reads in an axis n, a discrete axis. Here it is put as 0 is to 10 is to 1. These are the integers from 0 to 9 in the ascending order. So it returns a range of values from 0 to len. So likewise, I plot this against as a stem plot against axis. So here I will run this. Here you can see that the signal is a linearly increasing function. Here n equal to 0, it is 0, n equal to 1, it is 1, n equal to 2, the value is 2, that way. This is a function nun. Now let us try a triangular signal. Here I am concatenating a few arrays. That is, these are the range of values from 0 to n by 2 plus 1. Then I have another values list 1 to int of n by 2. Then I flip it. So what I have done here is, here it is the range of values from 0 to n by 2 plus 1, integer of n by 2 plus 1. So that is the ascending part of the triangular wave. Then this is the descending part of the triangular wave, the negative slope. What I have taken is, I have taken the values from 1 to n by 2, 1 to n by 2. Then I flip it by use this, that is star star minus 1, it flips the array. So here I have taken n equal to 11. So here I have an axis. Then I can make a stem plot. I will run this code. Here I will give a clear. Here you can see that this is a triangular signal. Here n equal to 0, the value is 0. It goes up like this. And at n equal to n by 2, here at the fifth value it reaches a peak. Then it is a descending function. So this is how I make a triangular signal. Now we come to the end of the video. Here what we have done is you have understood the different discrete time signals and you simulated them with Python. And that is the end of this video. I thank you all.